Okay, today is titrations. Now, titrations are, well, we're going to get into it. But basically, I have a little story to tell you guys about titrations. Once upon a time, I was a lifeguard. I was actually a lifeguard for about 6 years while I was going to school and university. And we would scoop up the water, and the lifeguards at that time were in charge of pool chemistry. And when we scooped up the water, we would put a chemical in it and slowly add a second chemical and then count how many drops were put in. And then when there was a color change, we would write down the amount of drops we put in and check this big grid. And it would roughly give us a couple different things that was in the water. Things like dissolved solids or like ionic substances that were dissolved. Because if it gets too high, it can wreck the pipes. Chlorine levels, because chlorine is what oxidized germs and bacteria. And pH. Well, pH was not really you could just put a couple drops in to get pH. But there was two things that we had to do, and they were like little mini titrations. Okay, let's talk about the practical application of titrations. What we've been doing so far, you might be like, only chemistry people need to worry about that. And you know what? Some of it is correct. However, anything to do with water in our world, if humans are using that water, it has to go through screening and tests to determine what's in it. Now, you guys in town get all of your drinking water from the Red Deer River. So when you turn on a tap and water comes out of the tap, or you're having a shower, that's all river water that has been treated at the waste treatment plant in Red Deer. If you live in the country like me, your water comes from underground aquifers that are water reservoirs trapped deep underground. And we had a water rig come out and punch a hole, hundreds of feet down into the trapped water, and the water came shooting up like a geyser. It was incredible. And then they tested the water for a whole bunch of things. Is the water safe? Does it have salts? Because some water in the ground is really, really salty, because Alberta used to be, most of Alberta and Saskatchewan was an ancient ocean. So they have to make sure the water comes up isn't too salty, because if you're drinking salty water, then that's bad for you, right? And it could also be other things in the water, iron. Also, then they used, how did they test that? They used titration tests, which we're going to be talking about today. So everything, even the water you drink that goes through the waste treatment plant, they do a titration of sorts to figure out if the water's good or not. You can find chemicals and chemical amounts by titration. All right, let's break down what a titration is. I've made these notes available so you can fill these in. These are important definitions, up to you, but they're available on the Friday lesson plan. Okay. A titration is carefully adding a titrant from a burette into another chemical called a sample. You do this super slowly and very measured, and you use highly accurate glassware. And the titration is the process of adding one chemical to another. Now, sadly, because of the apocalypse, none of you guys get to do a titration. And who knows what's happening in September. Zelensky and I are shooting a video for Monday where you'll get to see us do a titration, the lab that you guys would get to do. It's very sad. This is one of my favorite things for kids to do. It's a very important lab skill. So when things get back to normal, we're going to make sure you get a titration in. Okay. You stop the chemicals adding to each other when there's a color change. So without a color change, you really don't know when to stop. So sometimes we add acids and bases together and we have an indicator that changes color. Sometimes we add a chemical to another chemical that when it's gone, it changes color. Either goes clear or becomes a color. So you have to know when to stop it, and you stop it when everything is equal, or you've used up the sample. That's probably a better example, is you've used up the sample. All of the moles of the sample are gone. Okay. Now, in labs, we do titrations to figure out a standard solution. Okay. So if you want to use a solution for subsequent titrations, you need to first make sure that solution you're using is highly accurate. And that's called solution standardization. And then from that, you have a primary standard. Zelinsky and I are going to do that on Monday. We're going to make a primary standard through titrations. All right. This is a very bad drawing of a titration setup. There are these long, skinny tubes called burettes, and then there are these plasticky ends, which are like a nozzle with a little like valve. They're called a stopcock, and that's put into the tube, and that forms a burette. Below, usually in a beaker, more accurately probably in an Erlenmeyer flask, the sample is placed, and you have a tiny amount of it. Usually, this is the limiting, which means that you're going to run out of moles of that, and in the burette, you have the titrant, and this is usually your excess. So you have tons of this, and you keep adding this drop by drop by drop until there's a color change, and then you shut her down. Now, why does a titration work so well? Well, the cool thing is that you probably know the volume of the sample. Let's say it's 10 mils. Maybe you don't know its concentration. Maybe it's water from the ground that you're testing to make sure it's safe. The burette has gradation lines. As the water empties from start to finish, you can figure out the volume that you used to titrate the sample. Highly accurate. And hopefully you know the concentration of this. So when you know these three things, that's enough to solve concentration, like in the previous solution stoichiometry problems. Okay, here's a better example of what a titration setup looks like. Okay. All right, now a titration problem in the titration lab is set up with all of these different trials. You have to run multiple trials to make sure your data set is accurate. You can't just do one. You have to do multiple trials over and over and over and over again. And usually you'll have bad data sets. Now, just looking at this data, we can figure out a couple things. All right, from the initial and final reading, when we subtract that, we can figure out how much we used. So how much did we use in trial 1? Well, 13.3 subtract 0.2, we used 13.1 milliliters. In trial 2, continuing along the thing, we used 12.7. 38 to subtract 26, I get, 38.8 subtract 26, my bad, is 12.8. And 13.4 subtract 0.6, I get 12.8. Now, looking at the data, is there something that's not as accurate as the other? And I've got a little video to ask you to show you guys. So we're just gonna run that little video right now.
Hi ho, Kermit the Frog here, and Susan and I are just sitting here, and we're going to do a very favorite song for you. It's a time-honored old chestnut, that old favorite song that we all know and love so well, and it's called,
Three of these things belong together.
Three of these things belong together. Yeah, right. Okay. I'll do the first part of it. Yeah, and then you'll do the next part. Okay, here we go. Okay, everybody ready? Now take a look there. See that stuff there? Okay, now three of these things belong together. Three of these things are kind of the same, but one of these things just doesn't belong here. And now it's time to play our game. It's time to play our game. Okay.
All right. Which one doesn't belong? You do the exact same thing with titrations. Usually you have to do 4 or 5 titrations and you cross out the bad data. This is bad data. Its endpoint color, like where we've decided to stop, is not the same. Also, if we look at these three, they're way closer together. This one's out. You try to look for a plus minus of 0.1 milliliters in good trials. This is like if you're looking at a question. It will be a freaking miracle in the lab if you get that close. That's amazing if you get that close. It's kind of hard to get the exact same amount of liquid to the same color added because there's a lot of human error that goes into that. Now, why is it important to have multiple trials? Well, these 3 trials we would average together to figure out one of the pieces of data to do the math. Now, this is getting to be a long lesson, so we're just going to do one titration problem from start to finish. Okay, and it's the same thing. So the question says, what's the concentration of hydrochloric acid? So that's what the problems usually ask. They're asking to solve the concentration of something you don't know. Now, it looks like we have, what's the concentration of hydrochloric acid? I'm sorry. This should be, what's the concentration of sodium carbonate? Okay, because it gives us the concentration. Okay, it's just a typo, whatever. So we're mixing hydrochloric acid and sodium hydrogen carbonate. Now, the with part, when something is titrated with, if you think back to that picture, the with is in the burette. So all of